Hey guys, today we're going to be covering chemical reactions. So this is from chapter 4 of your book, the first two sessions. And this is going to be the end of the material that we cover before your midterm, which is next session. So this is for chapter 4.1 to 4.2. Chemical reaction, we talked about this when we talked about chemical changes, but it's a process by which one or more substances are changed into one or more different substances. And so the key here is that there's a change happening that's actually changing the substance from one substance to something completely new. A chemical equation represents the identity and relative amounts of reactants and products in a chemical reaction. And so when we're talking about a chemical reaction, the things on the left side of the equation are called the reactants, and the things on the right side of the equation are called the products. That's what's being produced, and over here this is what you're starting with. And so the reactants are always on the left hand side before this reaction arrow here, and then the products are on the right hand side. The numbers in front of the substances are called coefficients, and these are what we use to balance equations. If there is no coefficient, we just understand it as being a 1. So we've got reactants, products, we've got our elements, and then we've got coefficients that balance it. So a chemical equation must satisfy the conservation of mass. And so that means that whatever you start out with, you have to end up with that. And so that means that all of these elements must be balanced on each side of the equation. So here you can see that we use coefficients in order to balance it. And you can see that with this picture here. You can see the unbalanced equation, how many carbons we have, how many hydrogens, how many oxygens, and then on the other side. So we can't gain or lose anything. And so here it looks like if we didn't balance it, we'd be gaining an oxygen and losing some hydrogen, which we can't do. And so therefore we need to use coefficients in order to balance it. And so what we say is we'll make 2 oxygens there, and then we'll have 2 waters. And if you do that, then everything balances. So you can look at this element by element and see that it balances. This isn't making something up. This is just representing how it actually happens. And so when this reaction happens, it ends up being one molecule of this, which is methane, reacts with oxygen to form carbon dioxide and water. 2 molecules of that and 2 molecules of water. And so we're representing what's happening. The law of conservation of mass is occurring. And so this would be incorrect because here it looks like you're gaining or losing. This is what's actually happening when this reaction occurs. So when you're doing this, when you're balancing, we're never going to change subscripts because that would be changing something or making something up. Subscripts are what tell us what compound we have and how they are bonded together. So we don't want to change that because then we change the formula. What we would want to change are the coefficients because that just tells us how many we have. So it just tells us instead of 1 oxygen molecule, we have 2. Instead of 1 water molecule, we have 2. So we always just want to change coefficients. So for example, a lot of these, and there are different methods you can use. For these types of problems, I will give you a method that makes it easier, but some of these, it's just some trial and error. And so you can just play with it however you want. I'm going to go ahead and write down on each side what we have and how many we have, just to kind of get a feel for it. So we have calcium, we've got oxygen, we've got hydrogen, we've got nitrogen, and we've got sulfur. And then over here, we also have the same thing. So we have same elements on each side. So I'm going to add up what I have on each side. Here I have 1 calcium. And then here you're going to have to make sure you follow through with the subscript. So we've got 2 oxygens there. We've also got 4 right there. And so we've got 2 plus 4, which is 6. Hydrogens, we've got 2 right there, 8 right there. So we've got 10 of those. Just 1, or 2 nitrogens, and then 1 sulfur. Over here, 1 calcium, 4 plus 1, 5 oxygens. Here we've got 3 plus 2, 5 hydrogens, 1 nitrogen, and 1 sulfur. Okay. Where I like to start is by looking at these things that are an odd number and see if I can somehow make them an even number, see how that might help things. So we've got 6 oxygens there. Our oxygens are in that and that. And so what I'm going to try and see if I put a 2 right there, see what that does to the oxygen. And so then we've got 4 plus 2, which would be 6. So that actually balances that. We've also got the nitrogens. There's 1 there and 2 there. And we need to make the hydrogen even. And so the best way to do that is by putting a 2 in front of something, which works for the nitrogen. And so I think we might have balanced it here. And that changes the nitrogen to a 2. And then we've got 6 plus 4 is 10. And it's balanced. So some trial and error, looking at it to see what's right. And I will give you some practice problems that will help you with that. For anything here, this is called a combustion reaction. It's always where you start with some sort of carbon-containing compound, react it with oxygen. You'll notice that oxygen gas always exists as O2. It's a diatomic element, and it always forms CO2 and water. So you always see the products are always CO2 and water. And what I want you to do when you see these is first balance carbon and hydrogen, then balance oxygen. Okay, and so we'll see what I mean as I do this. So I've got CH and O on each side. Here I've got 2 carbons, I've got 6 hydrogens, 2 oxygens. I've got 1 carbon, I've got 2 hydrogens, and 3 oxygens. So I'm going to ignore the oxygens. The reason I'm doing that is because oxygen's by itself, and so I can play with that later and not affect more than 1 element. So I'm going to just balance carbon and hydrogen. So we've got 2 there, so I'm going to put a 2 in front of the CO2. And then for water, there's 6, so I'm going to put a 3 there. Now what I've done is I've made the carbons, and that's 6, the hydrogen's balanced, but now oxygen is 4 plus 3, that's 7. Okay, so if I want to put a coefficient there to make that equal 7, it has to be a fraction. And so even though I can't put a fraction, I'm going to do that. I'm going to say that I need 7 over 2 of that. And then what I can do to make it all whole numbers is just multiply the whole thing by 2. And so then I have 2, I've got 7, I've got 4, and 6. And so if you follow through with this, that's 4, 12, and 14. And then 4, 12, and 8 plus 6 is 14. So this is especially helpful when you get to larger problems where you have like C5H12, something like that, where it's really tricky to balance it if you don't have some sort of system. And so first balance carbon and hydrogen, then balance oxygen. I'll give you some practice problems with that, and so you can figure out how that works. Okay, physical states. Not always, but sometimes the chemical reactions will give you the physical states. These are some common ones that could be given. Solid would be a little S, little L would be liquid, G would be gas. And this aqueous, we will use that a lot in this session. It means it's dissolved in water. And this is for ionic compounds. And then we'll talk about why that's important, because the ions actually dissolve in the water. They break up into individual ions. So here you can see different physical states being used for this. You start out with all gases, end up with all gases. Here's another example. If you have solid potassium, you put that in water, that ends up kind of burning up and causing fire, and because it's a really exothermic reaction, and it produces a gas, hydrogen, and then aqueous potassium hydroxide that's then dissolved in the solution. So you can't see that, but it's aqueous. It breaks up into potassium and hydroxide ions. The gas that comes up is the hydrogen. And so this just tells us a little more about the equation when you're given the physical state. So here are some examples of that, where we're given the names and then we're going to write out and balance the equation. So for A, it says that solid potassium chlorate, and they give you the formula. It says KClO3, and they say it's solid, so it looks like that. Decomposes, here's your reaction symbol. It's decomposing to form solid potassium chloride. So potassium, that's K plus and Cl minus. So we've got KCl, and that is a solid. And diatomic oxygen gas. So just like before, I said that oxygen exists as a 2, and so it's diatomic oxygen gas. It exists as a unit of 2 oxygens together. Okay, so here is the equation. Now we want to try to balance it. So here I'm going to look, I've got 1 potassium, 1 chlorine. What's imbalanced is the oxygens here. And there's an odd number over here, and so I'm going to see what happens if I just put a 2 there. If I put a 2 there, I'm going to need to put a 2 there. And then that makes 6 here, and so I'm going to put a 3 there. So often 2s will help you to make something even, so that makes it 6, and then I can just multiply by 3 over there to get 6. So this should be balanced now. B, we've got solid aluminum metal. Solid reacts with solid diatomic iodine. So it reacts with diatomic iodine to form Al2I6. And so to form, that's our reaction symbol, just like over here, that was our reaction symbol. Al2I6. This is a solid. And so let's see what I'm going to want to do. This is a pretty easy one because these are broken up into individual ones. So I can just look at the aluminum, put a 2 right there. I've got 6 right there, so put a 3 right there. And then everything is balanced. Okay, so I'm going to cut this video off here so that you can go and practice balancing chemical reactions. I've included that in the practice section, and I have the answers as well. So work on that worksheet and then check your answers to make sure you've got it, and then come back and finish the notes with net ionic equations.